Hi everyone, welcome back. In today's video, we will discuss, let's use black, continue our discussion on oscillator theory. And today we'll look at something called the impulse sensitivity function. And it's sometimes called the ISF model. And I'll leave a link in the description for a reference from which I'm using for this video. So this is work developed by Ali Hajmiri and Tom Lee at Stanford in the late 90s. So let's get into it. So we saw in the previous video from limit cycles, just a quick refresher, that if I have some state space of, let's say, voltage and the derivative of voltage or the current, let's say in an LC resonator, V dot, then we end up with solutions sometimes which are these closed isolated trajectories called limit cycles, right? So if you haven't seen the previous video, you should definitely watch that before you jump into this. Okay, and then if you're, let's say, going along this trajectory in this direction, we saw that, any perturbation that is, let's say it's perturbed this way by some charge that's added into the system, then eventually this limit cycle will converge back onto itself. So it's a stable solution, and it only exists in two-dimensional or second order nonlinear differential equations, right? And we also saw that amplitude fluctuations are corrected in time. So it's not very sensitive to amplitude fluctuations, but phase fluctuations persist, right? So it has no memory of phase, but it has a memory of its actual amplitude because the limit cycle itself has a specific amplitude at each point in time. Okay, so that was sort of a quick refresher of what we discussed in the previous video. And we'll use some of this in today's video to develop this ISF model. Okay, so, typically if I have a regular, an ideal oscillator, then the voltage should take the form of some amplitude, cosine, let's say omega naught of t, plus some fixed phase, right? So this is an ideal scenario. But in reality, of course, you don't have this. What you have is the out of t is where the amplitude is a function of time. And we don't have exactly a cosine. We have some f of omega naught t plus and the phase, which is also a function of time. So I'll call this realistic. All right, where this f is periodic with a period of 2 pi. With period 2 pi. Right, this resembles more what we're talking about here, which is these limit cycles, right? It doesn't have to be a perfect circle. It can be sort of oddly shaped. It could be something like this, right? So we'll study this behavior of what these kind of limit cycles look like, and how to model them, okay? If we plot this in the frequency domain, so let's say this is omega, and I'm plotting V out of omega, then the ideal one would, in the real part of omega at least, would have a single tone, an impulse function. And this non-ideal one will have some kind of, looks like almost like a modulation on top of it, right? So it's not exactly a single tone, it has some spread. And this spread is generally characterized. So the spread is right here. This spread is characterized by what is called the single sideband noise spectral density. Okay. There are many other ways to kind of characterize the spread, but this is sort of the easiest way to measure it. So that's why this is generally used. So this is easy to measure, right? Using a spectrum analyzer. So if you write it mathematically, it's the equation of this total uh, spread, you could say, is a function of delta omega. I'll talk about what delta omega is. So it's given by 10 log of p sideband of omega naught plus delta omega 1 hertz divided by p carrier. So what do I mean by this? So let's say you have, you're looking at a spectrum analyzer and you have this kind of spread that you see, right? Then omega naught is the center and p carrier is the value here at the peak. Right? So here you're looking at the power spectral density. Call it S of omega of the voltage. Okay. Then at some separation delta omega, you pick a 1 hertz bandwidth. So this is 1 hertz. And you integrate the entire power inside this 1 hertz bandwidth. Right? And this is p sideband. And this gives you this total capital L, which is measured in dBc per hertz, dB with respect to a carrier for 1 hertz of bandwidth. That's the unit. So this is easy to measure, of course, in a spectrum analyzer. The only difficulty is that, of course, this L total is comprised of, this has an amplitude term and a phase term, right? I mean, typically the amplitude term kind of corrects itself because of this limit cycle behavior that we saw. And this L total is generally dominated by the phase term. And that phase term can be called L phase, delta omega, or just typically L of delta omega. And this is called phase noise. Okay, so that's sort of the definition. I'm going through this because the model we developed today, the impulse sensitivity function ISF model, is one of the models that is used to characterize phase noise or to quantify phase noise. It gives good intuition as to where it comes from and how to reduce it. It gives you also some design intuition for circuits, for low phase noise circuits. Okay, so let's actually look at the phase noise model. Okay, so given a system, we want to characterize or create a model for its phase noise, right? So this is some system. It has many inputs, so we can characterize, many noise sources, of course. So we can say, okay, each noise source acts like some kind of a small current source. Let's say I1 of t at some node, doesn't matter. And then we have another noise source, let's say, or many of them. I'll call this IN of t. So let's say there are n noise sources from different sources. It can be different kinds. I'm not specifying anything about what kind of noise sources there are, right? So let's say there are n noise sources, and at the output of at some node, we are looking at the amplitude and the phase. So that's the kind of system you have n inputs for n different noise sources, and at a specific output node, let's say the gate or the drain of a transistor in this entire system, we're looking at the amplitude and phase, right? So this is at some given node. Okay. What we can do is we can, of course, you can say that, okay, all of these noise sources are not at that same node that you're looking at, but they can have an impact at that node, right? So even though these noise sources are all over the circuit, all over the system, each of them has some kind of impact at this node of interest, right? Okay. So what we want to do is we want to create some kind of a mathematical model for this system. Right? So we can simplify it a bit. We can say, okay, we consider one noise source at a time. So let's say some I of t goes in to some kind of a system. I don't know what kind of system it is. And that produces a phase phi of t. Right? You can also say, you can separate them and say, okay, the same noise source goes through another system and then produces an amplitude of t. Right? And typically, this is not typically, I guess, but this is characterized as some transfer function, h of t comma tau, and this is ha of t comma tau. You can represent this as two different transfer functions, h phi of t comma tau and ha of t comma tau. Okay. What is tau here? So let's take a quick example. So let's say my I of t is an impulse, right? So if it is an impulse, then on the right-hand side, we should get what is called the impulse response, right? So this would be, so we send an impulse into the system and we want to see how the system responds to that, right? And tau is the time point at which this impulse occurs, right? So at 1 second, for example. And then we want to see, okay, at the same tau, how does this react? So let's say, okay, we can say, okay, the phase sort of has a step function, right? A unit step function. Why is that the case? We'll get into that in a bit, but let's just assume, okay, the phase has this kind of step function and the amplitude should have some kind of a damped oscillation, right? So the intuition behind why we assume that these are the models for the state, phase, and amplitude comes again from the limit cycle. So essentially, if I have an oscillation going on like this, and I introduce an impulse at some point in time, let's say if the impulse, is introduced somewhere here, then it sort of decays like this, and we can assume that it has, we'll clarify these assumptions more, but I don't know why this, yeah, essentially it does something like this. So the amplitude kind of, here we made a change only in the amplitude, and this amplitude kind of slowly corrects itself with time. And that's because it's a limit cycle, right? So we said that amplitude fluctuations have memory, so they come back and settle down on the limit cycle again. Whereas phase fluctuations, let me take a different color maybe. So if I make a change here, then this produces maximum change in the phase. And of course, we said that that doesn't really correct itself. So that's why whenever you introduce a step change in the phase, that step change persists. So that's why we say, okay, whenever there's an impulse, if that impulse creates some phase shift at tau, that phase shift persists. Whereas whatever amplitude shift it creates at tau, that decays with time. Right? So this is the intuition behind why that is. So given a limit cycle, any change in phase persists indefinitely. Maybe I don't have to draw it again. And a change in amplitude dies out. Right? So that's the sort of simplified model, I guess. Okay, another key feature that we can notice here, just from intuition again, based on what limit cycles behave like, you can see that, okay, impulse was introduced at a different time, then this response might be different, right? It could be small. Or if it was at somewhere here, let's say all these impulses are the same size, then this response could be something larger. Right? And you can kind of, let's maybe draw another figure to see why that is. Okay, so let's say I have my sinusoid like that. And the authors, at least in the paper, argue that if I introduce an impulse here, so only amplitude changes because the phase of this point and this point are the same, then the phase impact on the phase is zero or negligible. Right? Whereas if I introduce an impulse this location, right, then when it comes down, a lot of phase has changed. Right? So the impact on the phase is much larger. So that is sort of the heuristic, intuitive argument as to why it's a time varying system, right? This HA and HV are both time varying system, depending on when you introduce, depending on the tau, when you introduce this impulse, the phase and amplitude response, they change. Right? Of course, it's periodic because the system itself, the limit cycle itself is periodic, but within that period, it depends on when you introduce that tau. And that's a general intuition as to behind ISF as well. And we'll see what that is. So here what I've drawn essentially is T versus V of T, right? So we'll focus on phase. I'm not going to spend too much time on the amplitude part, of course, because that's not that important, right? We're trying to characterize the phase noise. So now I would like to plot T versus V of T. So the change in phase when these impulses are added at different points in time, right? Okay, so if you take this point, let's say this point, this point, this point, and of course, this is the same as the first one, so we don't have to take that. Okay, so we took blue color and we said, okay, when we added an impulse there, we saw that there is no change in the phase, right? So the phase response is basically zero. So I'll just draw a very small step function. And we said, okay, at this point, when we have the orange curve, the phase has moved ahead, right? So the phase response has some unit step function that is large. Then again, let's take a different color, maybe green. So let's say you add, a step down here, right? And the idea is that, okay, it kind of like doesn't have any impact on the phase again. So the green line would again be basically zero, but maybe slightly negative, right? And then let's take another color. How about red? Okay, this thing is going on. It's going on along the black curve. And then at this point, I give it a boost, right? Again. So when I give it a boost this time, it sort of, it sort of lags behind. Sorry, with a boost, and it sort of lags behind like that, right? Okay, which means that in this case, this unit step function has jumped back down, right? And you can see that this is somewhat periodic. So if I draw a curve through all of them, let me choose purple maybe. And we see, okay, this would probably look something like this. But if I just look at how much each step function's amplitude is, maybe it looks something like this, right? Like that. Okay, so this, how much each step function, the amplitude of each step function was, this is the ISF. So how sensitive it is to an impulse at the input, how sensitive is the phase to an input impulse excitation is captured by this term called the impulse sensitivity function. Right, so if I have a small impulse, let's say of some value, some amount of charge that you inject into one node, then you look at a different node or the same node and you see, okay, at different points in time during the period when I introduce this charge, how much amplitude, how much phase shift occurs that persists with time, right? This unit step. So what's the amplitude of this unit step? That's essentially what this impulse sensitivity function is kind of capturing. Okay, let's make that a little bit more mathematical. So we are trying to characterize the impulse response, HV of t comma tau. And we said that that's a unit step function that starts at tau, right? So that's u of t minus tau. And the amplitude of the step function is also a function of tau. It changes based on where you excite it. We'll call that gamma of omega naught tau. And it's divided by Q max, omega naught comma tau. Actually, there should be no comma. So it's just gamma omega naught tau. Okay. And this gamma is the impulse sensitivity function. We'll modify this a little bit later, but essentially that's what it is, right? And what is Q max? So Q max is the maximum charge displaced on the node of interest. This is just a way of normalizing this. So gamma becomes a dimensionless quantity. Okay, so that's what the impulse sensitivity function is. So essentially what we've done is we have empirically, or not really empirically, heuristically, I would say, we've said that, okay, given a limit cycle and its qualitative behavior, we said that this amplitude function should decay with time. And actually, let me use this. Said that this amplitude function should decay with time. Phase function should persist indefinitely. And we said the response of this phase function is a unit step function, and it depends on when the impulse comes in. So it's a time varying system. And yeah, it's a time varying system, and how much phase shift occurs based on when the impulse hits is characterized by this impulse sensitivity function, right? So that's essentially the model that we've created for this system. Okay. We made two big assumptions here, so let's clarify them. Okay, the first big assumption is that this system going from I of t to p of t, which is characterized by this impulse response, hv of t comma tau, you assume that this system is linear, right? And that's why it can be characterized completely by an impulse response. So what do I mean by that? I mean that when I of t scales, phi of t also scales by the same amount, right? So it's kind of a big assumption, but you can actually show that in most cases, this is true. True in practice, and I should say especially for noise analysis or phase noise analysis. Because I of t is small, right? So usually noise signals are small or weak. What do I mean by weak? I mean, quantitatively, I'm not going to give you a description, but just keep in mind that I guess this kind of noise input I of t is usually small, a small signal. And because it's a small signal, you can assume that the system is linear. And in the paper, actually, they do several experiments to show that, at least in those cases, it is indeed linear, even for very large or much larger IFE than what you would encounter in as noise for noisy signals. Okay, so that assumption is fine. But we made another bigger assumption, which is the basis of this model itself. So we assume that phi of t is independent of a of t and takes the form of a step function. Function u of t minus tau. So what do I mean by this? So we said earlier, actually, let's go back. So here, or here rather, here I said that, okay, when I have a function that grows like this, and you have an amplitude shift, it does not produce any phase shift, right? It just does that. That is not the case. I mean, you could have, for example, let me draw it in purple maybe, or black. Right? You could have, for example, something that comes this way. It has an amplitude shift here. Come on. It has an amplitude shift here, but that doesn't necessarily have to go through the zero crossing. I mean, why does it have to go through the zero crossing? It doesn't, right? It could go slightly off, and that could introduce a phase shift that persists with time. Right? Although at this point, there was no phase shift because only the amplitude was changed. There's no change in the location of time. Over time, a phase shift can build up, right? There's no guarantee that that doesn't happen. So you just kind of assume that. So let's go back. Another thing we've assumed is that, okay, whenever this impulse generates a phase shift. So we said, okay, it comes this way. And even at this location, it generates a phase shift. So generates a phase shift. So we said, okay, whatever phase shift is generated here, that remains fixed with time, right? We argued that based on saying that, okay, this is a limit cycle. It doesn't have any phase memory. So any phase shift that's introduced remains the same with time. But that may also not be the case, right? So essentially, this boils down to saying that the impulse response may not be a step function. So we assumed it's like this, but in reality, it could be 0 at the beginning and then slowly build up to some value, or it could be large and then decay to some value, or it could be large and then increase to some value. We don't exactly know what this function is. And to analyze a system like this without making this unit step function becomes somewhat complicated. We'll look at that in future videos. But essentially, that's what we are saying. So we are saying that, okay, if I have a unit impulse, it produces an exact step function. And that's the model we're going with, right? Okay. And there are advantages to doing that. Of course, it's not completely mathematically rigorous, but it is much simpler, first thing. And second thing, it leads to quite a bit of design intuition. And of course, for most oscillators that this has been tested with, as far as I know, turns out that it's not a bad assumption. It's a pretty good assumption. So, as engineers, as designers, as circuit designers, probably you don't care about being too mathematically rigorous. You care about what is useful. And as it turns out, this model has been very useful in many, many oscillator designs. But it's important to keep these assumptions in mind, back of your head. So these are the two assumptions that this ISF model makes. Okay, so with these assumptions in mind, we can go ahead and find an expression for the excess phase. Right, so we said, okay, we have this model, I of t goes into h phi of t comma tau, and that produces some phi of t, right? So we said, okay, this is a linear system, and we sort of argued that empirically. So now we can say, okay, what is phi of t? From linear systems theory, you can show that this is just an integral of the impulse response for different excitations, right? And this is fairly simple to think about. So essentially, if you have some input signal I of t, You can break that down into different impulses of different sizes, right? Each of them would have a response, which is different because it's all time invariant. So let's say the first one would have a response like this. The second one would have a response like that. The third one would have a response like this. Actually, here we've assumed they're all unit step functions, I guess. So first one like this, second one like that, third one like this, and so on. Maybe some go down, right? And you add up all of them, and that's what this integral is doing. And that gives you the overall phase, right, with time. So that's what this expression means. And then you can plug it in the form that we assumed, which is this one, right? Plug that in here, and that gives you 1 over q max, integral minus infinity to infinity, to t actually, because it's a unit step function, gamma of omega naught tau, I of tau, d tau. Okay. So now we know that, let me switch this to green. So we know that this is periodic, right? Because the limit cycle itself is periodic. And because that is periodic, it can be expanded in a Fourier series. Fourier series expansion of gamma. Okay. So let's write that out. So we have gamma of omega naught tau can be written as some C naught over 2 plus summation n equal to 1 to infinity Cn cosine n omega naught tau plus theta of n. Right, and this omega naught here is the limit cycle frequency, right? Or the period of this based on the is determined by the period of the limit cycle. Limit cycle frequency. Okay. Okay. So then we can plug this back in. So substitute into this. What does that give us? So that gives us, implies phi of t is given by 1 over q max times c naught over 2 integral of minus infinity to t I of tau d tau plus summation n equal to 1 to infinity. So I pulled the summation sign out of the integral. Cn integral minus infinity to t I of tau cosine n omega naught tau d tau. Okay. So essentially what this is saying is that if you know what these coefficients are, so what the Fourier coefficients are for any given impulse sensitivity function, that will characterize completely for you how much phase is produced with time, right? So given an excitation I, and knowing these Fourier coefficients C0, C1, and so on, will tell you how much phase shift is produced as a function of time. Okay, so probably for this video, I'll stop here. And in the next video, we'll look at how this ISF model can be used to get intuition into what is the process behind phase noise generation, especially close-in phase noise. So where 1 over f cubed term comes from, 1 over f squared term comes from. And this model actually gives you good intuition as to where those terms actually come from, right? So just to wrap up, we said, okay, we have a limit cycle. Do a quick review. So we said we have a limit cycle, and we looked in the previous video, we showed that they have amplitude fluctuations that are corrected, phase fluctuations that persist. And then we said, okay, we have a typical phase noise behavior for a real oscillator, characterized by this sideband, kind of single sideband noise spectral density, which is easy to measure. And it has an amplitude term and a phase term. We care about the phase term, which is the dominant term, because the amplitude term is somewhat corrected for. And this phase term is called the phase noise, right? It's easy to define, easy to measure. Sorry, that's how it's defined. And then we said, okay, we'll develop a phase noise model for this phase noise phenomena. And that's, in this case, we're developing the ISF model, impulse sensitivity function model. And the way it proceeds is that you have, let's say, a system, and that system has several, you can model all of the inputs to the system, all of the noise sources, the system as current sources, in different locations of the system. And we're looking at a single node, and we want to know what at that node or that net, what the amplitude and phase is as a function of time because of these noise sources, right? So then we say, okay, the first thing we can do is we can kind of assume the system is linear. So this is maybe, I mean, some of you may think this is sort of a contradiction. We said, okay, limit cycles come from a nonlinear system, but here you're saying this system is linear. Keep in mind that the limit cycle comes from a nonlinear system in terms of the differential equations that govern the voltage and current. That system is nonlinear. This system is different than that. So whenever you're talking about linearity or nonlinearity, you need to specify which system you're talking about, right? So here we're talking about the system that takes a current source input to a phase output. Whereas in the nonlinearity of the oscillator, we're talking about the voltages and currents, what kind of functions those are. So those in fact follow nonlinear dynamics, right? But this system is in fact, for the most part, linear, right? And it's shown empirically. So it's a good assumption. So once we say, okay, this system is linear, we can characterize it by its impulse response. So given an input I of t, which is an impulse function, we said, okay, the phase can be found by characterizing the system as two different impulse responses, one for phase and one for amplitude. And we said, okay, this is a time varying system, of course, because depending on when the impulse hits, the response can be different. And we assumed that the response takes the form of a step function, that whatever phase shift is created in the beginning, that persists for all of time. Big assumption, but turns out it's not too bad. It's pretty good. Leads to quite a bit of design intuition, which we'll see as we move forward in this lecture series, right? So essentially, we characterize it with this impulse function, impulse response, impulse sensitivity function, which defines what is the size of the step that is generated for different impulses at different times of the period, right? So that's what the impulse sensitivity function is. And then we clarified what the assumptions are, keep it in the back of your head. And then we defined, okay, given an impulse sensitivity function and its Fourier series expansion and an input current source, we can find what the output phase is. So this is the mathematical model of the system that we started to work with. So that's it. If you have any questions, leave them in the comments. In the next video, we'll look at how we can use the system to get a lot more intuition into phase noise. Thank you.